This presentation is delivered by the Stanford Center for Professional Development.
Okay. Any questions about last time? Our whirlwind tour through, or actually really like a sprint through convex functions. If not, we'll finish that up today. There's a ton of material here, and as I said last time, the important part is that you should get just the sort of the basics. Get the basics down, and then some of the more advanced stuff you'll get when you're forced to use it. Yes? Yeah?
When we were talking about matrix space and restricting it to a line to determine if it says convex, how do you ensure that when you add a multiple of a matrix, it will stay in that same space?
Oh, right. So the question had to do, we were analyzing convexity of a function of matrices, right? Which I forget what it was. I can look back here, but I won't. So of symmetric matrices. And we had to generate an arbitrary line in symmetric matrix space. And we did that by picking a symmetric base point. That was some x0, or I don't know how I labeled it. And then a symmetric direction. And that was this. Now, it's a subspace, or quite clearly, if you add a symmetric matrix to a scalar multiple of another symmetric matrix, you get a symmetric matrix. So this is a symmetric matrix. Now there, we also assumed, without loss of generality, that x0, the base point, was positive definite, because I think it was the log det maybe we were looking at, or something like that. So this was assumed to be positive definite, but v was not. V was a direction, right? So I don't know if I answered your question. I think I just said what I said last time, but how's your cognitive state? Is it improved?
So what you're saying, when you add a matrix into the same type as that one, you stay in that.
It's a subspace, absolutely. So it's a symmetric set of symmetric matrices, a subspace. I add a linear combination of a multiple of one to another. You're in the subspace. Yeah. Okay. Let's move on. And let me just remind you where we are, what the big picture is. So the big picture comes down to this. You're going to want to, well, two things. You're going to want to construct convex functions, but you're also going to want to deconstruct convex functions. And what I mean by that is that there'll be some function that's going to come up in some problem. I don't know what it is, medical imaging or optimal control. It doesn't really matter. And you're going to want to know, is it convex or not? Okay? And, in very, very rare cases, you will be forced to do this by hand. So by hand means you whip out your theta between 0 and 1, 2 arbitrary points, and try to argue this inequality. That's going to occur occasionally. If the function is twice differentiable, the equivalent of doing it sort of by hand, and by the way, every now and then you do have to do things by hand. So you will actually have to work out the Hessian. And it might be easy, might be not easy to establish that the Hessian is positive semi-definite. But in fact, the way you really want to do things is reserve these two for when there is no other option. What you really want to use is the calculus of convex functions to establish convexity. Oh, and for that matter, to decompose a function in front of you into a sequence of operations with the leaves of the tree being sort of atoms. An atom is a function known to be convex or concave or something like that. And here you want to know about the operations that preserve convexity. And we looked at sort of the really, really obvious simple ones. Non-negative weighted sum. That's kind of obvious. Composition with an affine function. That's also very easy to show. Pointwise maximum supremum. We looked at examples too, and by the time you get to sort of supremum, you can actually start showing convexity of some things that at first glance look pretty complicated. I mean, even with maximum, for example, to show that the sum of the 5 largest absolute values of entries of a vector is convex. It's not, first of all, it's not an obvious fact, and it's not that easy to show. It's like one line if you use a pointwise maximum argument. Then we looked at composition. That's where we are now, and I'll finish that off now. And I pointed out that, in fact, This is not a minimal list. And in fact, the minimal list, as far as I know, of the things covered here is basically like two. There are two operations that are used. Because composition actually subsumes non-negative weighted sum and pointwise maximum supremum. So, all right, so let's look at composition. The composition, the most basic case, it's the only one I actually remember, is the scalar case. So here you compose a function with another. And the question is, when does that preserve convexity? And the answer is, and it's the only one I remember, is a convex increasing function of a convex function is convex. Okay? And here, I do have to warn you, you're going to have to know that there is a subtlety. This is not a subtlety, interesting for its mathematical interest or anything like that. This is a subtlety that comes up in practice and will mess you up if you're not aware of it. And the subtlety is this. When you say an increasing convex function, the increasing actually refers to the extended value function. Okay? So, for example, you have to distinguish between, for example, x squared. Now, x squared is clearly not, x squared on R is obviously not increasing. Okay? However, x squared on R plus, if you restrict it to R plus, you would say, well, that's increasing. And in fact, any normal person would say, and it is indeed increasing. However, remember that if you define it to be undefined for negative x, then the extended valued version actually looks like this. And it actually assigns a value minus infinity. At this point, this function is by no means increasing. I mean, not remotely. It starts out at plus infinity, then dives down to 0. So that's non-increasing. Now, there is another version of this, and that's this. You take the square, like this, and then you assign it to be 0 below for x negative. Okay? This thing is actually increasing on the extended valued version is increasing this function. Okay? So these are things, unfortunately, you do have to know. They do come up. You can get deeply confused, and it can actually have real consequences if you don't, if you're not sensitive to this. And there's some irritating things here. Let me just show you one. Here's one. Let's suppose we want to look at something like, the norm of ax minus b to the 1.62. Don't ask me why, but we do. And we want to argue that that's a convex function of x. Okay? Well, you can work from the inside out, and you can say, look, that's an affine function. That's a convex function of an affine function, and therefore norm ax minus b is convex. Okay. Now what we want to do is say something like, well, this is a convex function to the 1.62 power. And I'd like to just say a convex function to the 1.62 power is convex. That's it's sort of true, but sort of like not true or something like. You have to be very careful now. All right. Now I can't just define, let's get my notation consistent, h. I can't just say h of z equals z to the 1.62 for z positive. I mean, I can say that. But the problem is this function here, I mean, this is, by the way, slang, or not quite slang. It's informal way to say that the domain is non-negative z. That's what this is. Okay? You cannot apply the composition theorem here. Absolutely cannot. Okay? So the correct way to do it is to say this. There you go. Is to define the function that looks like that. Okay? So that's the, and I know this is a little bit silly, but I mean this is very important, and it will mess you up if you don't, if you're not sensitized to these things. This is the function which is, it's 0 if you pass a negative argument to it. And it's the number to the it's the argument to the 1.62 power if you pass a positive argument to it. That function is actually increasing and convex on the its extension. Its extension is, and now I can apply this to this, and then I can make another argument. I can say, oh, hey, look at that. What I'm passing to the function h is actually always non-negative. It's a norm. But if you add it, therefore, this part, this case, or this switch in the definition of h never occurs, and so indeed we find that this thing here is convex. So I don't know if that makes sense, but that's it. Okay. So I didn't mention that last time, but I thought I'd just quickly mention it now. Okay, so let's look at composition. The sophisticated version is the vector composition version here. So if you have vector composition, it means the argument g is actually multiple functions. So let's say it's g1 through gk. So I'm going to take a vector function, takes many arguments of a bunch of functions. And again, the base composition theorem, or the canonical one that I remember, is a convex increasing function of a convex function is convex. And by increasing, I just mean non-decreasing. So it's just informal. So a convex increasing function of convex functions, I should say, is convex. Okay? So that looks like this. And the way, now when you prove these, making no assumptions, I mean, it's 3 lines, right? And you make no assumptions whatsoever about differentiability. But the way to sort of understand what happens is to write out the formulas. The same for the composition case, the scalar composition. So here, we'll take n equals 1. So the second derivative of f is equal to, this is just a chain rule for the second derivative of this thing. It's g prime. That's, of course, that's dg dx, which is a vector, times, and then the Hessian evaluated g of x times g prime. So that's a quadratic form. Okay? And then plus this thing. And that's nothing but sum. This is, let's see, partial h, partial whatever, it's ith component, evaluated at g of x, and then times g prime prime I of x, like that. Okay? And now you can see, for example, that we can check things out. If g is convex, this first term is non-negative no matter what. And then the second term, to be convex, you need, sorry, that's if h is convex. You need the g, if all the g's are convex, it means this vector is an element-wise non-negative vector that's interproducted with, I don't know if that's a verb, but it is now. You interproduct that with the gradient of h. If h is increasing, that's a non-negative vector, and so this thing is positive too. But now you can see that there's actually other ways to construct things. So, for example, a more sophisticated version would go something like this. I'll see if I can get it right. All right, a convex function of a bunch of others is convex, provided. Okay, now let me see if I get it right. I'll stare at this thing. Provided, for each argument, either the argument itself is convex and h is increasing in that argument, or the function, the argument, is concave and h is decreasing. Did that? I think that came out right. Okay. So, by the way, there are people who know these things and memorize them. Not memorize them, but they have very good mnemonics or something like that. I'm not one of them. I just redo this whenever I see it. Whenever I have to deal with it, I go somewhere quiet or find a little piece of a whiteboard or paper and just write out formulas like this or something. So, okay. So this is vector composition. Okay, and we looked at some examples last time. Okay. One more, and this would pretty much finish off the basic operations that preserve convexity of functions. And this is minimization. Now, by the way, we've already seen that there's a sense in which maximization, there's not a sense, sorry, maximization preserves convexity. So and we've already seen that. That's the maximum, pointwise supremum. Notice that in the case of maximization, there is no requirement of any kind on how the variable you're maximizing over enters into the function. Right? Everyone know what I'm talking about here? So the point is that if I have a function of 2 variables, f of x, y, and I want to look at something like this, let's say, and define that, I'll try to get my notation right, as g of x. Okay. This thing, the only requirement here for convexity of g is the following, is that for each y, this function is a convex function of x. Period. That's the only, for that matter, this thing does not have to be convex. It doesn't even have to, this doesn't even have to be like an Rn or even be a vector space. It could be an arbitrary set. So supremum over a completely arbitrary family. So if you maximize, well, assuming you can, when you maximize, there's no condition, I mean, nothing matters as to how y enters into this function. Okay. Now, minimize also works. Now, that's a bit weird because generally what you're going to find out with all these things is that there's these weird asymmetries. In other words, you know, it's that you can do one thing but not the other. The cool part, well, why we have this class is it turns out often the thing you can do is the thing you often want to do. So that's otherwise this would be interesting but not useful. What's interesting here is that it's very rare that you can sort of both maximize and minimize something like that because they're sort of like they have opposite flavors. But in fact you can, but it's a much stronger condition. Here's the condition. You can minimize, some people call this partial minimization, by the way, because full minimization would be to minimize f of x, y over x and y. You can minimize over a variable provided, and the result will be convex, provided, this is very important, f is jointly convex in x and y, and the set C over which you minimize is convex. Okay? And then this is easy to show and all this sort of stuff. So let's look at some examples. Here's a very basic one, and it's one you may have seen before anyway. Let's take a general quadratic form and block the variables into two groups, x and y. So that's a general quadratic form. It's the quadratic form associated with this matrix, A, B, B transpose C, block. All right. Well, we know that f is jointly convex in x and y, provided this full block 2 by 2 matrix is positive semi-definite. Okay? By the way, when is this function convex in x for any y? What's the condition on A, B, C, D?
A is positive semi-definite.
Precise. It's only that A is positive semi-definite. There's no condition whatever on B and C. So if I were to take this function here and maximize f of x, y over y, the result would be convex, provided only that A is positive semi-definite. Yeah?
I was wondering, on what condition on A could you then state that that function was not convex?
On what condition on A could... which function? F. Okay, in this case, because it's a quadratic form, it's necessary and sufficient. So if this matrix here has one negative eigenvalue or more, it's not convex, period. And not only that, we can easily produce points. I can make you a line where instead of going like that, it will go like that. Actually, you tell me the line. You tell me the line.
What makes it go like that?
Yeah. You have a quadratic form with one negative eigenvalue.
Eigenvector associated.
Yeah. Take the eigenvector, you sail out along that line, and it'll go like that. It'll go down. So, and that pretty much ends the discussion on convexity for that function. Okay. All right. Now, if I minimize this function over y here, and what we'll do is this is just a technical condition. This actually works with C positive semi-definite. In fact, I'll tell you what happens when C is only positive semi-definite. When C is positive definite, you minimize over y. Yeah, you can do this analytically because then you take the gradient and you set it equal to 0 and all that. And you end up with this. Then you find the optimal y, you back substitute that into this form, and what you're going to get is this thing, x transpose times A minus B C inverse B transpose. Now this is the Schur complement, so which you maybe have seen before. If not, I assure you on homework 3. Is that right? Yes, homework 3. You'll see it because it's just a good thing to know about. So that's called the Schur complement of C in the big block matrix. So that's the Schur complement. And that's convex. And you know what that tells you? That tells you this matrix has to be positive semi-definite. So you may have seen this somewhere in some other context. Maybe an estimation or I don't know where, but it would come up. Well, it would come up in mechanics and come up in all sorts of things. This Schur complement here. Yeah?
Joint convexity just means the graph is convex?
Joint convexity means that if you plot sort of x and y, then it's bowl-shaped, the graph. Okay. Convexity in x means that if you fix y you know, and sort of look at a slice, it would go like this. It would go up. And they could be quite different, right, the two. Okay. Here's one. The distance to a convex set is going to be, the distance to a convex set is convex. By the way, that's a rather complicated function. I mean, it's not simple. So if I draw some convex set like this, let's just get a rough idea of, I mean, the set is everything in here. Let's work out what the distance to it is. What's the distance in here? 0. Now, I can draw the level curves of the distance. So, for example, I might end up, I won't do this right, but you know, you get the idea. It would look like something like that, right? That these would be all the points with a certain distance from here. And then as you move out, actually, of course, these get smoothed out, right? So if you have sharp corners in a set, then the distance level curves get smoother, right? I mean, here. Like that. So you'd get things that would look like this. Let's see if I can do it right. That's like actually circular. Is that it? Yeah. So I think that's it. This is just to give you a rough idea. So this function, though complicated, is convex. Okay? And the argument would go something like this. You'd say, well, let's just take a look at this thing. I look at norm x minus y. Here, I take norm x minus y. I have to make this is a very important argument. That's jointly convex in both x and y. That's the critical part that allows me to do this. Okay, so that's going to be convex. Okay.
How do you say that? That's jointly convex in x and y?
Here. Yeah. Let me give you the full proof. Okay. I mean, I could get out thetas and stuff and do it by hand, but I don't want to. So I'll show you the snappy proof. Snappy proof goes like this. I have two variables, x and y. What kind of function is x minus y of x comma y? Yeah, it's affine, sure, but it's linear, which is stronger than affine. But affine's good enough. You're absolutely right. Therefore, this is a convex function, the norm, of an affine function of x and y. That's better than whipping out the thetas, wouldn't you say? Yeah. So, what's that? It's actually linear, but affine is good enough to establish convexity. Okay. We'll look at the last example of this one is sort of on the borderline between sort of, you know, basic methods and more advanced ones. Although it actually comes up in more applications than you think. That's the problem with these things, is you look at something, think it's esoteric, and then by the time you look at enough problems, you realize it actually does come up. So that's the so-called perspective of a function. So the perspective of a function is it's a transformation. It does this. It takes a function from Rn to R, and it's going to produce a function which has one more argument. So it's going to be a function from Rn plus 1, or if you want to explicitly make it a pair, Rn cross R to R. And it's this. It's g of x and t is t f of x over t. So it does a weird scaling. It scales x first, and then it multiplies by t. Okay? So that's the big, and that's a function jointly of x and t. Here. So, you know, obviously for any fixed positive t, this is obviously a convex function. Because, you know, x over t is linear, therefore affine, f is convex, and then you multiply by positive constants. That's clearly the case. Maybe it's less obvious that when you fix x, t f of some vector divided by a constant is convex. Maybe that's less obvious, but okay. And showing this is not hard. By the way, as you might guess, the perspective of a function is related to the perspective of a set. So, and there is some connection between the epigraph of this is sort of, you remember that one of the only maybe not obvious transformation of sets that preserves convexity, right, was the perspective transformation. So not surprisingly, the perspective of a function is related through epigraphs to that. But I won't go into the details. We'll just look at some examples. Here, X transpose X, that's the sum of xi squared. Well, that's obviously convex. But that says that T times x over T transpose x over T, which when the T's cancel out, is x transpose x over T is convex. Okay? So there you go. Your quadratic over linear function is convex, and we got it by a quick perspective operation on just the norm. So we went from, we took something that was completely obviously convex, ended up with something where this is less obvious. Okay, so you start with negative logarithm, and then you form t f of x over t, and you end up with t log t minus t log x, and you actually get that this is convex on x and t. So, and it's kind of, some of these things like if you fix x, for example, this is linear in t, so that hardly matters, and you get the negative entropy over here. It's not so obvious that this is jointly convex in both x and t. And by the way, from this you can derive the various things like negative entropy, Kullback-Leibler divergence, and all that kind of stuff. So, okay. Another example would be something like this. If f is convex, then g, which is an affine, this has to be positive, affine positive function multiplied by f of a general linear fractional transformation, but with the denominator required to be positive, that's going to be convex. So, and that's on the condition, that's where this is in the domain of f, when C transpose X plus D is positive, and this image point is in the domain of F. So that's going to be convex. Okay, so by the way, I recognize fully that none of this is motivated and all that kind of stuff. So don't think I don't. Okay. We'll look at a couple more concepts. One is the conjugate function, which is going to get heavy use later in the class. But actually not for a couple of weeks. But then it'll get very heavy use. So this is just going to be your first glimpse at it. It's the conjugate. Oh, I should add that all of the things we're doing are these are completely standard things. I mean, these are not weird esoteric things. I mean, they're like the conjugate, everyone knows what it is. It's got slightly different names. Some people call it the Fenchel conjugate, and there's all sorts of other names for it, depending on how fancy you want to sound when you use it. But these are just completely standard concepts here. So I'll let you know when we deviate into something that's not. So, okay. So take any function, convex or not, and you define the conjugate function, that's f star of y, and that's the supremum of y transpose x minus f of x over x. And so let's see if we can figure out what that looks like graphically. It looks like this. You form the graph of f here, and then you form this function yx. Well, we'll just do this in one variable. So I form a function where the slope is y. So that's y, the slope here. And then it says, I want to maximize the deviation between these two functions. Well, one-sided deviation. Anyway, so I want to see how much smaller does f get than this line. And here, you would see that that point occurs like right here. And that's going to occur, by the way, when if it's smooth, when this thing is tangent. Actually, either way, it's going to occur when it's tangent to this graph here, like that. And then this point will give you the conjugate function here. So this gives you a very good way of working out the conjugate function. For example, if I decrease y slightly, what will f star of y do? Or to be more convenient, let me ask you, what will minus f star of y do for this function? This just requires you to visualize. If I decrease y slightly, what happens here? Well, I change the slope, okay? And then I go down here, and I'll make a point of tangency. It'll shift down a little bit, right? Or to the left. Well, down and to the left. And this point of intersection here will creep up a little bit. Everybody agree? So in fact, minus f star will increase slightly, so f star would decrease. Now, by the way, what happens as this slope changes. There's a critical moment here. And the critical moment occurs right there. Everybody see that? So at this very critical moment, something interesting happens. I draw a line here, and that would sort of give me that value of the conjugate there, negative value. Now, as y decreases further, what happens? This gets interesting. What happens is the point of contact leaves here, shifts over here, like this, and this thing now starts going down. Everybody see this? Okay, so this is your first chance. When we do duality, you'll get tons and tons of chances to do visual exercises like this, but this is your first exposure to this idea. So this is the conjugate. Now here's an interesting fact about a conjugate function. It is convex. The f star of y is convex in y, completely independent of whether x is convex or not. I'm sorry, f is convex or not. Totally independent. And it's, really stupid. Look at this. What kind of function is what's uncovered there above my hand and to the left, right of my finger as a function of y? It's affine. That's affine in y for each x. Hey, that's a supremum over affine functions. That's convex, period. So this function is convex. Okay. Actually, I can tell you something fun. I'll go ahead and let you. I'll mention it now. It's fun. Now usually you've seen conjugates, right? You've seen conjugates for complex numbers. You've probably seen conjugates in some other. I mean, there's a bunch of places worked. But when someone uses in a mathematical context the word conjugate, there's some sort of cultural background there. A conjugate is usually something which, when applied twice, does what? I mean, we're just talking roughly, right? If you do a conjugate twice, what do you get? Kind of the original thing, or something. And if you've seen this in a lot of different other contexts, it might be something related to it, like the closure or something like that. That would not be surprising, the conjugate. So you might guess that the conjugate of a function would be an interesting thing. And you might even guess it was the function. But I'll tell you what it is, and it's super cool. This is just for fun, I'll tell you what it is. Here's a function, okay? And the conjugate of the conjugate is not the function. It's something called the convex envelope of the function. And it is let's see if I can say it right. It's the largest convex function that fits under this one. I think I said that right. Okay, so in this case, here's what you do. In fact, I can describe in terms of epigraphs very easily. Ready? It's this. Let's see. We have to have a name for the convex envelope. So f_env is going to be the the function which is the convex envelope of f. And I think I can write it. I hope this is going to work. There we go. It did work. Okay? So I don't know if that's clear. This says that you take the epigraph of a function and you form the convex hull of it. And that's the epigraph of the envelope. So let's sketch here the convex envelope of this function. Well, it's going to look like this. It's the function itself out here. It turns the corner, and then it goes like this. Ooh. Ignore that. And then it hugs the function again. Make sense? So that is what, just if you're curious, this is. It'll come up. You'll see later. So that's what it is. Okay. Oh, by the way, for a convex function, roughly speaking, f star star is f. Okay? Roughly speaking means that there's some technical conditions and things like that. Okay. Let's look at some examples of the conjugate. And this is actually a calculation you're going to have to do a bunch of times. It's going to come up in duality and things like that. So you're going to have to do conjugate calculations. So I'll just do one, and then I quit. And then you'll do some, I promise. And then that'll be enough. Then after that, you'll do it on demand when you need to. So the negative logarithm is convex. Let's calculate its conjugate. Now, of course, I can calculate the conjugate of the logarithm if I want. I can calculate the conjugate of anything I like. But we're interested mostly in conjugates of convex functions. But anyway, so let's take a look at this function. So this looks like this. I guess that's the negative log, something like that. That's the negative log. And I want to work out the soup or maximum over x of xy plus log x. Now, log x, of course, is unbounded above. So obviously here, if y is 0 or positive, this thing is unbounded above. So this supremum is plus infinity. Okay? So that much is clear. Now, let's assume then that y is negative. This is interesting because now it's a log, that's growing, but then you subtract a linear thing, and in fact, a linear thing will win out on a log always. And they will, to find out exactly where it reaches its maximum, you just take the derivative. It's a, these are smooth things. So you take the derivative of xy with respect to x, and you get y plus 1 over x is equal to 0. That is the point x that would maximize xy plus log x, provided y is negative. Okay? And so this says that x is, 1 over minus y. Okay? And that's good. Then you plug this x back into xy plus log x, and you get minus 1, that's the xy part, plus log 1 over minus y. Okay? And that's this thing. That's the conjugate. And that's for y. And it's important when you work out a conjugate to get the domain correctly here. So, okay. If you have a strictly convex quadratic, so that's 1/2 x transpose qx. By the way, the 1/2 is here because the 1/2 is there often because it simplifies some formulas or makes them look prettier. Other cases where you're not like basically calculating gradients, you leave the 1/2 off, and it's sort of your choice. Actually, this is one of those Fourier transform-like things where you can stick the 1 over 2 pi, anywhere you want. And of course, everybody does it differently, which is a pain in the ass. So, but okay, so it's one of those stories. But if you put the 1/2 here, you're going to get something pretty. So if you work out the supremum of y transpose, I mean, this is a quadratic function. Set its gradient equal to 0, you get x and all that, and you get a beautiful thing that the conjugate of a quadratic function associated with positive definite matrix Q is the quadratic form with positive definite matrix Q inverse. So that's what that comes up in. Conjugate, by the way, has all sorts of interpretations, but I put them off until, like in economics and things like that, I put them off until we get to duality and we get to cover everything on this. Okay. Quasi-convex functions. So I think we have only one more of these, and then we're done. You're done with your first dose of convex functions. I should let you know there's like a whole industry. In fact, almost like a little subculture of it's been going on for like 40 years, where people work out little variations on convexity. So there's quasi-convexity, there's pseudo-convexity, and I forget, that goes on and on and on, and keeps otherwise dangerous people off the streets. So it provides a positive. The net benefit to society, I believe, is positive, and it's fine. They're harmless people. They're nice enough, but. Just to warn you, you would find tons and tons, and they get, of course, all bent out of shape, and they make little diagrams, right? This shows what implies what, and they go, huh, did you know that a strictly quasi-convex, blah blah blah, is actually pseudo-normal convex? Or anyway, and they'll draw diagrams, and if you don't adequately say, wow, that's really interesting, then you'll be in trouble. So that's the best thing to do. That's my recommendation when you are confronted with someone. Also, by the way, someone who pesters you and says, did you mean quasi-convex or pseudo-quasi-normal, strictly convex? Or I don't even know what they do. You can look on Google to find out all the different things. Anyway, so we have looked at all of these things, the 27 different extensions, and identified 2 that seemed above threshold. So anyway, this is one of them, quasi-convexity. So quasi-convex is this. It's a function whose sub-level sets are convex. Now, of course, any convex function satisfies that. But that's not enough, And here's an example which is obviously not convex. But every sublevel set is. So what happens is here, to get a sublevel set, you just put a threshold. You know, I really should put it above like that because you want to look below. Or I don't know. Well, okay. You need a fishing line to put across here. And you pull it across here. And you can see, for example, the alpha sublevel set is an interval. The beta sublevel set, I mean, assuming that this continues indefinitely, is actually a half-infinite interval, but it's convex. So this is fine. And you call something quasi-concave if the superlevel sets are all convex. So let's just look at some examples to see how this works. Square root of absolute value of x. I guess that's a function that looks like that. That's quasi-convex on R. I mean, it's obviously not convex. It's quasi-convex because you just simply put a line anywhere and you get an interval for it. Here's an interesting one: the ceiling of a number. So the ceiling of a number is it's the smallest. Let's see, it's the smallest integer that's bigger than the number, bigger than or equal to the number. That's the ceiling. So now this is pretty weird because that's integer valued, okay? Now integer valued functions, for example, well, let's have a discussion about integer valued convex functions. Who would like to start the discussion? What can you say? Let's discuss the theory of integer valued convex functions. Do they exist? Constant, yeah, okay, so there. For example, here's a function, ready? 3. Convex, right? Okay. Let's keep going. Anything else? 4. Thank you. Okay. This is going to be a long discussion at this rate. Okay. What do you think? By the way, I'm not asking. I don't want a proof. We're talking eyeballs here.
Because it's discrete.
Yeah. Okay. So it can't. So these are the only ones, right? The only integer valued. It couldn't have 2 values. Like it couldn't have 3 at one place and 4 at another. Okay. So that was you are now in total command of the extensive theory of integer valued convex functions. Basically, there hardly are any other than they're known as constants, actually. Okay. Now, so that's why this is a bit interesting. That the ceiling is which is obviously integer valued, and it's going to be quasi-convex. And actually, what's kind of cool about it is we will be able to optimize things involving these. Okay, so it's going to come up where you will. I absolutely promise there'll be problems involving like FIR filters. Again, if you're in EE, and we'll ask questions like, what's the minimum order required to have 1 decibel ripple over this passband, minimum 40 decibels rejection over here. Now, when you just hear that question, the convex part of your brain is not lighting up because you just heard order of a filter. That's an integer. Being familiar with the theory of integer valued convex functions and knowing that that's a very short theory, you might say, well, there's no way you can optimize something involving an integer. Well, you can. So we'll get to this. So, okay. So that's quasi-linear, and it's easy enough to check. I mean, these are just stupid things. Every ceiling, the sublevel set of a ceiling function is just an interval. I mean, so it's very easy. Let's see. Okay. Log is quasi-linear. Product x1, x2. That's a quadratic form. That is neither convex nor concave. It is this. It's the quadratic form associated with that matrix. That matrix, just take a look at it, it's not positive definite, and it's not negative definite. It's got split eigenvalues. So it's neither. It's certainly neither. Quasi-linear means it means quasi-convex and quasi-concave. Right. And by the way, these functions do not have to be linear, not even remotely. So, okay. So a linear fractional function is quasi-linear, meaning it's both quasi-convex and this is the most famous, by the way, because this function here is absolutely not convex, right? If you have a linear fractional function, it looks something like this. Well, there might be a place where it goes to minus infinity or something like that, but it's going to look like this, like that. Oops. I drew the wrong one. It doesn't have to look like that. All right, I take that back. It can be, depending on A, B, C, and D. sorry. But in general, it doesn't matter. A linear fractional function is going to be quasi-convex and quasi-concave. So this is actually there are famous problems that have this form. Okay. Here's an interesting one. Distance ratio. So the ratio of your distance to 2 points on the set of points where you're closer to one than the other. That's, of course, this is a half space, by the way, which I think, yeah, it's a half space, right? So as long as you're closer to one thing than another, then your ratio of your distance to that than the other is actually going to be quasi-convex. By the way, all you need to do is take this function and put a gamma, take it to the gamma, like if you're in wireless, and you have here the SIR from a good transmitter and a bad one. And it says, well, you have the inverse SIR. And it says that the inverse SIR is convex, quasi-convex, provided you're closer to the transmitter you want to hear than to the interferer. Okay? So, sorry, I have to throw these in because I'm bored. Sorry, go on.
Is it the same set of convexity preserving operations that works on these quasi-convex things?
No, that's what's cool. It's not. It's a more general set. So for example, a monotone function of a quasi-convex function is quasi-convex. Because quasi-convex just basically says, all that matters is your sublevel set. So if I put some monotone transformation, it works just as well. Yeah, so it's a different set. Oh, and it's neither a restriction nor a generalization of the others. For example, the sum of two quasi-convex functions is generally not quasi-convex, right? And let's just look at a quick example to show that. Here's a quasi-convex function. Here's another one. And the sum, for sure, is not. Oh, there's another name for quasi-convex. It's called unimodal. That's another name, right? What reminded me was I added these two together in my head, and that's what we would call not unimodal. Yeah, so that's what, okay? Okay, so let's look at one that's not non-trivial, just for fun, is the internal rate of return. So here, I have a cash flow sequence, so x0 up to xn, and then xi is a payment in period I, and that's positive means to us, okay? So we'll assume that x0 is negative. That means that we pay out at period t equals 0, and we'll assume that the sum of all of these things is positive. So I guess that's what we call a good investment. So meaning that that the sum of if these are positive, it means it's a payment we receive, and this is the sum total of everything, and it's balanced out by our investment. So minus x0 is the investment. Then, if I work out the present value of this cash flow stream with an interest rate r, then that's nothing more than this. I sum from I equals 0 to n xi with 1 plus r to the minus I. Okay, so that's my present value, assuming an interest rate r. Okay, now the internal rate of return is defined usually completely incorrectly and ambiguously in fact essentially every text I look on in finance. It actually said not the smallest, it said it's the interest rate that makes the present value 0. Well, let's see. I would say somewhere in middle school you would learn that, for example, like a function like that could actually have a 0 there are many values of r for which it can be 0. But this apparently hasn't stopped people from defining it as the. So the correct one is it's the smallest interest rate, which makes the present value 0. So that's the definition of the internal rate of return. So for example, internal rate of return is 8%, means that your cash flow stream has a present, or let's say the income derived from the cash flow stream is exactly the same as had you invested it at an interest rate of 6% or 8% or whatever I said. Okay, so that's the idea. Okay. Now this is a rather complicated function of x. right? So in fact, even, well, I mean, I guess not of a particular one, but you know, if you have a whole bunch of different cash flows and things like that, this is it's quite complicated to visualize and the way you would visualize what the internal rate of return of a cash flow stream is, I guess you really have to just sort of form this sum. That's a function of R. Note that it's a function of powers of 1 over 1 plus R. So it's a polynomial in 1 over 1 plus R. Okay? Then you'd find the roots of the polynomial. These would be the values of the interest rate at which that investment is neutral, and then you'd find the smallest of those. You know, this is complicated. It's like an eigenvalue or something. This is not simple. Okay. It's quasi-concave. Okay. Notice, by the way, this is your first hint that something cool is happening. Let me mention it because it's the first time we ever hit it. We're going to find things like quasi-concave functions we're going to be able to maximize. You'll be able to maximize this, 5 lines of code. Okay? With complicated constraints. You'll be able to maximize this. We can minimize convex functions and quasi-convex functions. We can maximize quasi-concave ones. Now, turns out it's hard to minimize internal rate of return. That's a very difficult problem. What this says is it's actually easy, at least algorithmically and mathematically, to maximize internal rate of return. Now, if you think about it carefully, in practice, we're not neutral. Problems of maximizing and minimizing internal rate of return do not occur in with equal frequencies, right? Actually, pretty much, you never want to minimize internal rate. You want to maximize internal rate of return, and you go, "Wow, look at that! The thing we want to do turns out to be the thing we can do." I just thought I'd mention this because it comes out this, you know. I mean, it's kind of stupid. You don't mention this in like 263. You say, "Isn't that amazing? We can minimize norm AX minus B." Every now and then we want to maximize it. Anyway, well, okay. I just thought I'd mention it. So how do you show this? Well, to show something is quasi-concave, you look at the super level sets. By the way, what you're doing is you're saying, please, let's study the set of cash flow streams that have an internal rate of return exceeding, let's say, 8%. That's what by the way, that's a rather complicated set, right? That's like the set of symmetric matrices whose eigenvalues are less than whose maximum eigenvalue is less than 7, right? I mean, it's not impossible to imagine what it is, but it's quite complicated. Okay? So what is it? Well, let's see. To say that your internal rate of return is bigger than R, that means that for all interest rates up to R, your internal rate of return I'm sorry, your present value is actually positive. Okay? So that's this. That's an infinite set of inequalities, one for each interest rate up to capital R. Okay? So I'll let you check this, but it's a quick way to see this. By the way, if you tried to do this, in cases of like, a sequence of 2 or 3 using the formula for the roots of a polynomial or something, this would not be fun. Okay. Now for quasi-convex functions, there's a modified Jensen's inequality, and let me just draw it because it's better to draw it than I don't know what's here. So Jensen's inequality, of course, says something like this. You have 2 points like this, and let me just draw a convex function first. And it basically says that if you draw this line, this chord lies above the graph. That's what Jensen's inequality says. It says actually you do a better job. For example, f at the midpoint is smaller than the average value of f. So, I mean, that's basically what it says. That's convex. Quasi-convex is cool. Let me draw. There's a nice quasi-convex function. And I'll pick some points. I'll pick this one and I'll pick that one. Okay? So, oh no. Well, the chord lies above it. Sorry. I picked a bad, it doesn't matter. In this case, the chord would lie above it. But I'll draw the picture of what you have to have for a quasi-convex function. Instead of the chord, what you do is you draw this thing at the maximum of the 2 values. So it says the function has to lie below there, which it does. Okay? So another way to say it is if you have a quasi-convex function and you have one x and you have another y, and you form a linear convex combination of x and y, and you evaluate f, it's no worse than the worst of x and y at the endpoints. That's the way to say it. If worse means large in f. That makes sense? So this is the picture. It's the map. And the way you write that is this way. That when you form a blend and evaluate f, you're no worse than you couldn't be worse than f at the endpoints. Okay? That's the picture. And you have some things like this. If f is differentiable, and if it's quasi-convex, this occurs if there's a characterization here, and it basically says this, that if it says that the sublevel set of f lies on one side of the gradient picture. So if you take the gradient like this and form a half space, it says everything over here has a higher or equal value of f. That's what it says. Okay? So, or another way to say it is and for a quasi-convex function, every point that's better lies on this side of this thing, period. Okay, that's another way to say it. By the way, that's a hint that we can minimize it, right? Because when you evaluate a gradient and it gives you a half space and it says, I don't know where the minimum is, but it's got to be in this half space, you can think of that vaguely as a query. By evaluating a gradient, this is very vague and weird, but it basically says you got one bit of information because it basically said it's in that half space, not that one. So we'll get to that later, but that's why this would work. Okay. And finally, in our whirlwind tour, our last, the second of the two extensions and variations that were above threshold. Hey, this one is very simple, but it's important enough. I mean, it's not like it's an extension or anything. It just happens a lot. And it comes up. It's log concavity. Now, this is weird because it turns out, to say something's log concave just says log f is concave. That's all it says. Yeah, and it says, it's a weird thing. It says that if you evaluate the function at a point on the line segment between x and y, it's bigger than or equal to the weighted geometric mean. It's the same as if you just take logs here, right? You get this. Now, for some reason, applications come up overwhelmingly log concave, not log convex. I don't know why, but it doesn't matter. I'm just telling you. Log concave things come up all the time. Log convex things never come up or almost never come up. So it could be that in all the applications where where this thing comes up, which is statistics, it's everywhere in statistics. We'll see it's in lots of things. But everywhere where it comes up, their conventions are that they want to maximize things. Like you want to maximize likelihood ratios and maximize posterior probabilities and things like that. So I don't know. All right, that's it. So here are some examples. Powers are log convex for positive positive exponents, and log concave for negative ones. And this is very, very important. Lots and lots of probability densities are log concave. Okay? So that's very important. And that's called a log concave probability distribution. A log concave probability distribution. Okay? And an obvious example would be a Gaussian. Because if you take the log of this thing, and let's look as a function of x, you get a negative quadratic. Okay? So another one would be like an exponential variable or a Laplacian variable with a two-sided exponential distribution. But actually, tons and tons of distributions are. So if you're in statistics or something like that, all various families, all the ones you can probably think of right off the bat would be log concave. Like things like beta distribution, pretty much everything. Chi-square, all of these things are going to be log concave. And by the way, the log concavity is going to be the basis of a whole bunch of bounds in statistics. So if you're in statistics, this comes up, and it might even have been mentioned explicitly, although I doubt it. Actually, who here? I know there's people in statistics here. They're not gonna self-identify though. I'll find out. I can find out who's in. Anyway, who's anyone who might have been in this ever? Has log concavity ever been mentioned in the statistics? Yes. Cool. What class?
Oh, in seminars. I don't know if it's been mentioned.
In seminars. Oh, okay. Not in like, how about 310? No, it wouldn't be in 310. It would be in the statistics stuff.
In 300, it's mentioned in passing.
Cool. Good. Okay. There we go. So, great. Okay. Here's one. Totally non-obvious. Has amazing applications like just immediately. Is the cumulative distribution of a Gaussian. So it's got different names. I think ERP-C. I think in EE and communications they decided that it wasn't good enough at this already name, and they called it the Q function or something. Is that correct? Something like, isn't that what that is? Yeah.
1 minus.
1 minus. It's what?
Q is equal by minus.
1 minus phi. Okay, great. That's good for my colleagues to introduce a new notation for something that's been used for hundreds of years by many other people. Sorry, let's move on. So the log of a cumulative distribution, and I suppose the log of a Q function, is log concave. Okay, and you know this is not so obvious. You know the cumulative distribution looks like this of a Gaussian. You know, it goes like that and then goes up like that, like that. Okay, so looks like that. If you take, it's obviously not concave. You take the log, and the part that's 1, well, that's 0, obviously, when you take the log, and this part curves down like that. And it's asymptotic, in fact, to something like a square here, which is the asymptote of the Gaussian, the tail of small values here are well approximated by a Gaussian itself. No, that's false. I'll tell you very shortly.
They're quasi.
Which are? All which?
They're all quasi, but they're not. I guess.
In one. Yes, that's true because they're monotone. Right. So, yeah. So they're definitely quasi-convex. Okay. We'll get to this. So let's look at some properties of these things. Well, just by working out what the Hessian of the log of a function is, it's something like that with this thing side or something. You get this. It says basically, it's actually quite interesting. We can look at it. It says that f of x, oh, by the way, if you're talking about a log concave or log convex function, obviously the function itself has to be positive, or non-negative at least. Okay? It can be 0, by the way, which in log will map to minus infinity, which is perfectly okay because for a concave function, minus infinity is essentially our OOD token. I gave it another name the other day. That was out of domain. What did I call it before? NID. Anyway, one of those tokens. It's the token for being out of the domain. So minus infinity. So this is non-negative, and this is actually quite interesting. I mean, I guess you could put the f of x over here or something like that. This says to be, of course, to be concave is to say that the Hessian is less than or equal to 0. This says actually the Hessian can be less than or equal to. That's a rank 1. That's a dyad. So this actually says you're actually allowed one positive eigenvalue in the Hessian of a log concave function. That's cool. One positive eigenvalue you're allowed. So it means you have one direction along which your curvature can actually be positive. We needed that because, well, look at this. Okay? But it's got to be overwhelmed by, it's got to be no more than something having to do with the gradient here. I mean, I don't want to give too many interpretations of this, but okay. Now let's look at, here's some obvious things. Product of log concave functions is log concave. Totally obvious because the product of two things, you take the log, it's the sum. So that's the sum of convex functions. Sum of log concave functions is not always log concave. That's easy. Add to make a mixture of Gaussians, moved apart, you get two bumps. Oh, by the way, if it's log concave, it's quasi-concave because log is monotone. So, and you can't have two bumps on a quasi-concave function because then a super level set will be two isolated intervals. It won't be convex, the set. Okay. Now we get to something which is highly, highly, highly non-obvious. It's this. If I have a function of two variables, and it is log concave, and I integrate over one of the variables, the result is log concave. It's true. Okay. By the way, for literally years, I have looked for a simple proof of this. And simple means like, simple, assume everything you want. X and Y can be one variable. F can be differentiable as many times as you like. So I'm not talking about a simple proof that would please our careful mathematician friends. I'm talking about just for a normal person, where you just write out the first and second derivatives, look at some stuff, and say, and you end up with this, and say, there it is. I'm just talking about something, a bunch of calculations that would establish it. I have failed always. By the way, people, I've said this challenge out to a bunch of people. Said, please come up with a, and several times people have come up with, by the way, I have a 4-page one, which is very complicated, and anyway. So, by the way, so if anyone ever finds one out figures out a simple one for normal people that just uses calculus or something like that, and a couple of arguments here and there, it'd be great. But after which, I will say that it was obvious. But at the moment, it's obvious but unknown to us. This simple proof. It's certainly not known to me, that's for sure. So it's not obvious. The implications, though, are stunning, and I will show you some of them. Convolution preserves log concavity. Okay? So, now, by the way, that gives you a lot of stuff right there. So, if you have convolution, it means if you have two random variables, each with log concave density, and you add them, the distribution of the sum, obviously, is going to be log concave. So that's the kind of thing you would get just right off the bat. Okay, so convolution preserves log concavity. And here's a fascinating application is this. It says if you have a convex set and you have a random variable with log concave PDF, then the probability, this is a function of x, that x plus y is in C is log concave. And the way to show this is I just apply this one integral. Your integral thing is that's the big hammer. You just reduce everything to the one, as of now, non-obvious fact that you can integrate over one set of variables a log concave function, and the result is log concave. So roughly speaking, integration preserves log concavity. And you would apply that to, you'd make a function here, g of x plus y, which is just the indicator function. It's 1 if you're in the set and 0 if you're outside, and work out this integral, and it's that. And this is very cool. This immediately has amazing applications, of which I will show you one right now. So here's the way it works. I have some set of values like this in some multidimensional space, like that. And these are, you should think of these as acceptable values of what happens. So each axis could be, it doesn't really matter. This could be I'm setting the process recipe or the target process recipe or whatever for making ICs. One of these could be threshold voltage, which if it's too high, the chip is too slow. If it's too low, it dissipates too much power. By the way, how many people here are in circuit design? Because no, come on. Does anyone even care about it? They're here. Maybe they just sleep late. That could be a tradition. They were in the clean room until very late last night and couldn't make that. Because I know they're in this class. So, all right. But if no one is here, then I'll remove these examples from the. All right. All right. So this is the acceptable. And what's going to happen is you're going to set a target thing you're going to set the target value like that. And you'll adjust all your manufacturing to hit that target value. By the way, when you do manufacturing runs and you look what comes out on Monday, Tuesday, Wednesday, Thursday, and things are biased away from this point, if the mean of that is away from that point, you need to get a new people running the manufacturing because you would offset it. So we can assume that when you hit the target point, the distribution of values what will actually come off in manufacturing will have that mean. I mean, if it doesn't have that mean, then you shift it or whatever. So, all right. So you have a mean, and let's say that the manufacturing perturbations are given by this random variable w. Okay? Could be some horrible thing, some joint distribution, but we assume the following. It's log concave PDF. I mean, Gaussian would work this instantly, right? But that's it. Now, what's going to happen now is this. It means that when you hit a target here, you're going to get values around, like that or whatever. Every now and then you'll be out. If you're out, then that's something that doesn't perform. That's something that's no good, and that's a waste. And your yield is the probability that you actually end up in this set. This all makes perfect sense. Okay. Now, imagine taking the target and moving it around. As you move it around, your yield changes, obviously, right? So, for example, if you put the target here, what would the yield be? I'm not endorsing that as a choice, by the way, but what would the yield be here? Would it be 0? No, probably not, because every now and then, accidentally, you would manufacture an acceptable part. Right? No, I mean, if the distribution doesn't have finite support. So every now and then accidentally. And this would be a poor choice. And it's totally obvious what a good choice is. You want something deep in the set. And that's got all sorts of names. It's called design centering is one of the names for it. And yield optimization. It's got all sorts of other stuff. Although yield optimization means something different in other contexts. So, okay. Everybody got this? So, and now you should also be able to visualize also the yield as a function of the target point. Okay? So it's high here, low here, less low here. And high is somewhere at some point in the middle here. So here's the point. That function is log concave. Okay. Just very roughly speaking, let me tell you what that means. It means we can optimize it. We can maximize it. So put these two together, and what it says is you can actually directly maximize yield. So can you make a note? We'll make a homework problem on that. Not for homework 2. Later. Don't worry. But don't worry. We'll do a yield maximization problem. Okay, so that's it. Okay. One last topic on convex functions is convexity with respect to generalized inequalities. Generalized inequalities allows you to overload, ordinary inequality. All you need to define convexity of functions is you need the ability to talk about in the very general case, you need to talk about the line segment between 2 points. We'll work in vector spaces, so for us that's fine. Then you need this inequality to be able to say that like f of theta x plus 1 minus theta y is less than or equal to theta f of x plus 1 minus theta f of y. And so you need that inequality. These can be vector valued, and then you can talk about convexity with respect to a generalized inequality. The only case where this would really come up and is actually anything interesting is with matrix convexity. And so there it just says the inequality holds, but the inequality is to be interpreted as in terms of matrices. So now I think we'll quit here. This sort of finishes our whirlwind tour through the flora and fauna of convex sets and functions. Next time, half of the lecture will be a little bit boring because it's just nomenclature of optimization. But by next week, actually, I think things will get interesting. So we'll quit here.